All right, this is our notes for stats for 1.3, describing quantitative data with numbers. So how do we talk about numbers? All right, so in the first one, we're going to talk about mean, which should be familiar to you. So mean is the average of something, right? So it is the average of something. Okay, but it gets a little bit more complicated than that in that it is actually called X bar. That's how we say X and that bar above it. That's a symbol we use in stats for the average. Not a big deal. Okay, so how do we find it? We take the sum, so we add up all of the observations. So all of those numbers. And then we're going to divide it by the total number of observations. So if they give us 3 numbers to work with, then we're dividing by 3, okay? So the official formula looks like this. X sub 1, that just means the first number in my list, plus X sub 2, plus X sub 3, make a pattern, plus dot, 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 plus when we get to the last one, we don't know always what the last one is, so they call it sub n. And then we're going to divide that by n. So we're going to add up all the numbers and then divide by the number of the numbers. Another way to write it is with this big E, which just means the sum of. Okay, so we're just going to add up. And what are we adding up? We're adding up all of the X sub i's, and then we are dividing that whole thing by n. Okay, so that's another way to write it. All right, so we're going to assume this is a sample. Later, this will become more important, but we're looking at, is this number coming from a sample from a bigger group, or is it everything? Okay, so when we're thinking it's a sample from a bigger group, we're using that X bar notation. We'll use a different notation when we're talking about the big population of everybody in the whole wide world. So we always assume that this is some random sample of something else. Okay, so population is everything or everyone, and a sample is part of a population. So you'll see them talk about, samples. This is the result from our sample, okay? That's what that means. All right, interpret in words. So now we're starting to talk about being really specific in stats about using the right phrasing for stuff. So when they say that the mean is 12 flowers, what is that? How do you explain a mean to everybody? You can't just change it and say it's average. That's not good enough, okay? So it's almost like that share idea back from elementary school. You would say something like, if everyone in the sample had the same number of flowers, it would be 12 flowers. So we're basically saying if you shared it with everybody, everybody would have 12 flowers, but really some people might have more, some people might have less. Okay. All right, so another thing about mean is it's a balance point. Okay, so we're not going to go and grab that pencil and ruler activity, but I'm going to basically show you the same idea. Let's say that I had a balance or a seesaw or something from a science class that helped me measure stuff, right? And on it I stacked, let's say, 4 objects right here and similar 4 objects right here, right? It would balance. And where would it balance? It would balance right there in the middle. Right where that little triangle is right there, right? Okay, but what happens to that same balance if I leave these alone? These are still there 4, but these, there is now 4 and they're now spread out this way. If I want it to balance, do you agree that that triangle, that balance point, needs, it's called a fulcrum in science, has to move? Which way does it have to move? Well, if you know anything about seesaws, you know that you always want to move out a little bit, right? If you're trying to balance with somebody who is a different size than you. So we would have to move it a little bit closer to this side, okay? So what does that mean? Well, it's the same visual idea of mean being a balance point, right? So here, the middle is just adding up all of those observations and I end up right there. Here, if I add up all these observations, there's a lot more bigger ones, and so my mean tends to be closer to the bigger side. Okay, that's the main idea of what a mean is. All right, so now we're going to switch over and we're going to go and talk about median, which is another measure for data. Okay, so median, the symbol for that is just a capital M, just to make things super annoying. So X bar for mean, just an M for median. Okay, now the formula is a lot more, kind of have to explain it in steps versus just writing it out. Okay, so here is the main idea. Okay, I'm going to make this a little bit bigger. All right, step number 1, put all the numbers from smallest to biggest. So put them in order from smallest to biggest, from small to big. Okay, second step, we're going to count up how many numbers are on the list. Sometimes if it's a lot, they'll tell you in the title of the question. So I'm going to say that the total is n. So if the total is odd, then that means it should be the middle number. Come back. So we just find the middle number. And if the total number of numbers is even, well, then that means I'm going to have 2 numbers in the middle or no numbers in the middle, depending on how you look at it. But we want the 2 numbers in the middle. So we are going to average. So we're going to take a mean of the average 2 numbers. Average the middle 2. Okay. All right, so that's how we find it. So let's give an example to this. Here's our example. We have a 4, a 4, a 7, a 9, an 8, a 2, and a 3. All right, so let's go ahead and put them in order first. So that is going to be 2, 3, 4, 4 again, 7, 8, and 9. And then off to the side, I'm going to count up how many of those are. That is 7, so n is 7. All right, so if I want to find the middle, I have to find the middle of 7. So there's 2 ways to look at this. I could cross them out slowly in pairs and say, here's one, here's one, here's one, here's one, here's one, here's one. That one in the middle has to be my median. Okay? You just have to make sure you cross them off in pairs. Or I could look at this and say, if I divide 7 by 2, I'm going to get 3.5. So that means I have to go to the number after 3. So the 4th number should be it. Okay, and that's if there's a 1 in the middle. Okay. All right, how does the median change if we add 1 more number to the list? Let's say that we added 1 more 8 to the list. So if I put another 8 in here, what would happen? Well, the 9s would cross out this way with the 2. This 8 would cross out with the 3. This 8 would cross out with the 4. We now have n equals 8 numbers. Right? So the middle number for that I would have between 4 and 5, 4th and 5th number would be the middle numbers. So I would have 4 and 7. So 4 and 7 I'd have to add together, divide by 2, and I would find it's a 5.5 would be the median. Okay, what else would change for this? Well, what happened to the original median? Which way did it go? Well, because the number was bigger, it moved a little bit to the right, so we went from a value of 4 to 5.5, so it increased slightly because 8 was higher than the original median, right? So basically, it's like imagine people are standing in the line and they carry these numbers. If we add 1 more person into the list, basically everybody just moves over a little bit and we go, okay, now where's the new middle person? Well, it moved over a little bit too in the same direction where we added people, okay? All right, so mean and median. When we're comparing them, which one changes more from an extreme value being added? So imagine we have that same little list of numbers and we added in 100 or did something along those lines. Okay, so let's make it an even easier number to figure out. Let's do 3, 4, 5, 6, 7. Now why I like those is because except for the middle number, all the partner pairs add up to, wait for it, add up to 10, right? So this adds up to 10, this adds up to 10, so this is a 25, right? So if n equals 5, we have a median of 5, and we also have a mean of 5. If I add these all up, it's going to be 25 divided by 5, right? So right now, they're all in the same place. So what happens if I add 100 to that list? So what happens if this one, if there's 1 more at the end and it's 100? Well, what would change? Well, the sum would go from 25 to 125, And then instead of dividing by 5 for a mean, I would divide by 6 for a mean. So that is going to be like 20 and 5 leftovers. So now X bar is 20 and 5 leftovers. What's going to go on with the median for that? Well, since we have 100, let me mark them off. 3 would go with 100. 4 would go with 7. And now I have a median that is 5.5. So which one moved more? Well, the median went from 5 to 5.5, but the mean went from 5 all the way up to more than 20. So which one is more extreme? More extreme is definitely the mean. Okay, so mean is an extreme mover when there are extreme numbers. Okay, so if it's an extreme mover, we are going to call that not resistant to change. If it was resistant, resistant would mean it's stuck, right? It doesn't move much. So this mean is not resistant. So how would we clean? It's not as resistant as median, at least. So complete the words. Which one is more resistant than the other? So resistant means it's stuck. It doesn't want to move as much. So we would say median is more resistant than mean. Okay, now that's going to be an important fact later. If a graph looks symmetric, then we're going to describe mean and median to each other like this. Let's go take a look. Okay, if it was symmetric, so let's say I had a graph that was all uniform, every single bar in it was uniform, and let's say that this was a 6, right? Well, then the median would equal the mean, and they'd both be 6. They'd be exactly the same thing. Let's take a look if they're skewed. And I know on the last recording in some of the Edpuzzle questions, I could have asked that question about skew better. So let's make sure we've got that part cleaned up. Okay, so looking at skew, this one says it is skewed right. Skewed right means that's where it trails off to. It trails off to the right. So if I'm looking at a graph kind of like that, it would start out big, bold, lots of numbers, lots of values, and then it would suddenly taper off to very little, right? So that would be skewed right. Okay, so it looks something like that. Well, if I found median, median would still be in exactly the same place. It'd kind of be in the middle number. But what would happen to the mean? Well, in this part, we're thinking about lower numbers being more. So the mean would move lower since it's not stuck as much. So the mean would be more over here, and the median would be more over here on it. Okay, nope, I did those backwards. Hang on. Okay, let's do that one more time. Got these guys over here. All right, so these end up being the outliers, right? They're the ones that are the extremes. These are not the these are the regular dudes. We have lots of them, okay? So if I'm adding outliers, I'm adding high numbers to my mean. So that's gonna move my mean further over this way and my median more over this way in relation to each other. I don't have necessarily the exact spot for them, but the mean is going to be closer towards the outliers because if we put in really big numbers on a number line, if this is 0 and this is 2000, right? We've got a couple numbers over at the 2000s that is moving that mean over to that side, okay? If we're looking at a graph that is skewed left, so the tail is longer on the left side, okay? And let's say I smooth it out a little bit and it looks something like that because it's got lots and lots of data and I don't want to draw every single one, right? All right, so it's skewed to the left, so there's more numbers that are extreme over here. So we'd have median over here. It'd be like the middle dude. The middle dude is probably in this top spot here. And then X bar would be somewhere down here because they'd get pulled to that side because there's a few outlier numbers on that side. The bulk of them would be over here, okay? And again, if it would be symmetric, even if it was a curve, if it looks something like that, then we would expect the mean and the median to be in the exact same spot, okay? All right, so that's the relation between mean and median. So there are times where we like one and there's times when we like others, and we'll talk about that in a second. Okay, so we've done mean and median. Let's talk about the other measures we can talk about with numbers, which is the spread of numbers, okay? So range of numbers. We have to be really careful about this, okay? We typically, in everyday language, I've even done it already in this course so far, we say things, we say the values, I see some 2s all the way up to some 5s or something like that. If we use the word range, you have to be very careful, especially if it's in the question to find range. If you are using range, you have to remember it is a calculated number. It is not from here to here. It is, range is highest minus lowest. So you're basically saying my numbers span a distance of 12, or my numbers span a distance of whatever it is. So we're going to do range for this one. So we're going to say that range is equal to 24 minus 3 is going to be 21. Right? So 21 is the distance between our lowest, that's horrible, our lowest and highest values. Okay. All right. Next thing we're going to do is we're going to figure out how to capture quartiles and graph those. They're going to lead us to a different type of stats graph that we really like. So in order to do those, we're still looking at a list of numbers. Here's the steps to find quartiles, okay? And we're going to use it with this example down here. So I'm going to fill up a lot of the space around here. All right, so how do I calculate a quartile? We're going to put the numbers in order, again, from lowest to highest, just like we were finding median from before. Matter of fact, that's the first thing we're finding. So on this one, the first thing I'm going to do is I'm going to put them in order. So I've got 2, 3, 4, 4, 7, 8, and 9. So they're exactly the same as before, right? So since n equals 7, I know there has to be a middle number because it's odd. And since there's 7, it's got to be 3 on the left side, 3 on the right side, and 1 in the middle. So this one right here is our median. Okay, that's the first thing that we find for number 1, is you find the median. Okay, next thing that we want to find are the next 2 quartiles. So to do that, we're going to ignore that median number. Okay, so we're going to ignore that one median number. We're going to break it up into this one on this side, this one on this side, and now we're going to find medians of the halves that are left over. So on this side, there are 3 numbers. So if there's 3 numbers, there should be a middle number. So this number right here becomes quartile 1, first quartile, because it's the lowest, so first quartile. And then the same deal over here, this becomes quartile 3. Okay, all right, so again, if there's one number in the middle, you do not make it part of the next part to find quartiles. You just say that's my median, and we go ahead and we break them out. All right, so what's left with that? Well, there's a couple other numbers that we want to do. So we just found Q1 and we found Q3, and then it says the max value is Q4. So this number right here is Q4, and this number right here is actually Q0, but nobody calls it that, Q sub 0. So what they actually call it is, we call Q sub 0 the minimum, we call this the median, we call Q4 the maximum. Okay, and then we have the Q1 in there and Q3. So why are they called quartiles? They're called quartiles because they hold what percent of the data set? What percent is a quartile? It's going to be 25% of the data, right? So if I look at this, I should be able to basically split them into four groupings, 4 houses for the numbers themselves, okay? All right, so let's go and calculate the ICR. Okay, so ICR only comes from a 5-number summary. That's the only place where we ever use it, okay? And it is also a calculation. It is the interquartile range. Another way to say that, it is the middle 50%. So that means it is the distance from Q1 to Q3, and the calculation for that is IQR equals Q3 minus Q1. I'm going to put those lower and make them subscripts. Hang on. Q3 minus Q1. Okay, so it's just the distance between the middle 50%. Okay, all right, so taking a look at that, so now we have those. Let's talk about resistant for these new numbers that we looked at. So remember, resistant means stuck. How likely are they to be stuck in their spot and move very little, if at all? Okay, so when we did a mean and we added in 100, it moved a lot. So I'm going to say not resistant. I'm going to put a line through R for us, just for shorthand. Okay, median we know doesn't move much. At most, it moves 1 person to the right or left when you add in an outlier, and often it's finding the average between 2 numbers if they're different. So we're going to say these numbers generally stay put. These are resistant. Okay. What about IQR? Well, since it comes from that list of people, right? Again, Q1 and Q3 are not going to move that much when you bring in one outlier. They're going to maybe move one half over one way or another. So this one is resistant. It tends to be stuck. And then what about range? Well, range we get from max and min. So if I add up another humongous large number to the list that wasn't very large before, the range is going to get humongously large, right? So this one is not resistant. Okay. All right, so there was a question over the past couple of days of like, what is an outlier? So let's talk about what the outlier rule is. We have a mathematical rule for testing if something is an outlier. Okay, so the thing that we're going to test to see if something is an outlier or not is a simple calculation. Okay, so the first thing is, here's the rule. If one or more of your points extends past 1 higher than 1.5 times the IQR number, remember that's just a subtraction, plus Q3, or lower than 1.5 IQR, and that's a minus problem, so hang on a second. So this one is going to be Q1 minus 1.5 times IQR. Okay, so is 2 in our example an outlier or not, and why? Well, let's go back and we have to go and figure out what the IQR is of this number above. So to find IQR, we had to do Q3 minus Q1, and what were those numbers for us? It was 8 minus 3, or it was equal to 5. 5 was our IQR from that list of numbers, right? Okay, so let's go see if that ends up being an outlier. Let's go see what we have. So we have IQR equals 5. To make my life easier, since it's in both formulas, I'm going to multiply 1.5 by 5, and I'm going to get 7.5. So I have that 1.5 times the IQR already figured out. Okay, so 2 is at the high end or at the low end? It's at the low end of the data, so I want to check the low end. So I'm going to check Q1, which was a 3, minus 7.5, and figure out what that equals. If it is more than where we were, so this is going to be negative 4.5. So what this says is anything lower than, anything left of, anything lower than negative 4.5 would be an outlier. So what do we know about 2? Does it make it past the border? No, it has to get past 4.5 for it to be low. So this is not an outlier. So 2 is not less than negative 4.5, so not an outlier. So you can imagine it's almost like an imaginary wall that could be anywhere in that list of numbers, and then anything past it in either side would be called an outlier. Okay, so 2 is not an outlier. All right, here's how we're going to use all those numbers. So again, 2 is not an outlier. Okay, so 5-number summary. So these are the main things that we just got from all the quartiles. So I know quartile says 4, but there's really 5 sections in there if you think about it, right? What's the first one? It's the minimum. It's actually Q0, right? And then we have Q1, and then we have the median, which is Q2, and then we have Q3, and then we have the maximum, which we really wouldn't call Q0 and Q4, but those are our 5 numbers, okay? All right, so how do we make a box plot? This is a way to show these 5 numbers visually so that people can compare them to other 5 numbers, right? So we're going to plot all the points for all the 5 numbers in the 5-number summary. So we're going to go take those numbers from the previous answer, or they're going to give us new ones. Let's see. They're going to give us new ones. Okay, and then just a reminder about quartiles. Again, quartiles. Quartiles. Okay, it represents about a quarter of the data. So that means 25% of the numbers fall within this range. Okay, or what fall within this section, this, I don't want to say range because it's an actual calculation right now. Okay, so let's go and figure out how to make a box plot. So we're going to show you. First thing is we're going to get all those numbers in a number line. We already have them, that way they're already ordered for us. We're going to get our 5-number summary from it. So I'm going to switch colors here and let's go find our 5-number summary from this one. So what do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So to find the middle of that, there's going to be one number in the middle, and it's going to be the 5th number in the middle. So 1, 2, 3, 4, 5. So 8 is my median. Okay, then I'm going to break up the rest of them, leave the median out of it. Okay, and I'm going to do the same thing for the remaining parts. So there's 4 on each side. So when there's an even amount in the middle, we're going to have to average them. So this is 1 plus 5 is 6. 6 divided by 2 is 3. So 3 is Q1. And over here, the midway point or the midpoint between 11 and 13, right? We add those up, we divide by 2, we get 12 is Q3. Our maximum is 20. Our minimum is 1. All right. So let's go do a number line. Now remember, number lines can be x-axis or y-axis. It doesn't matter as long as you're sticking with the lower numbers on the left, higher numbers on the right, or lower numbers down below, higher numbers up top. I'll do this one as horizontal because I feel like I'll have more room here. So what I'm going to do is I'm going to create a number line for all of those numbers from 1 to 20. So I'm going to say 0 is right here, 20 is right here. I'm going to try to break them down really quickly here. 5, 15. Okay, and here's what we're going to do first. It says once you've got your 5-number summary, you're going to create a central box, or we're going to put a line down for where the median is. So the median is at 8, 6, 7, 8, 9. So this one is 8. So I'm going to put a line right here at 8 for the median. Then we're going to create a box out of it by containing that little bar in between Q1 and Q3. So we're going to go from the number 3, 4, 3. And up to 12, 11, 12. And we're going to create a box. Okay, so something like that. All right, then the next thing I'm looking at is we have the line that marks the median. I actually did that one first. And then number 4 is we're going to make the whiskers of a box plot. So a box plot, or sorry, box and whisker plot, right? Often has whiskers, I've heard it called that, or just a box plot. All right, so the next thing we're going to do is we're going to go put a dot at each one of the minimum and maximum points. So the minimum was a 1, so I'm going to go put a dot here, and the maximum was a 20. I'm going to go put a dot here. If you have minimums and maximums that go outside of that box, you would attach them with little lines that go straight through the middle. That's called a whisker. Okay. All right, now in number 4 in the directions and in the rules, it says extend from the box out to the smallest and largest observations that are not outliers. So this would be just a regular box plot. It would not check for outliers. We can do that in a minute, and then we'll modify it and see if they need to be outliers in there or not. Okay, so this is what a box plot would look like horizontally. Imagine if you put it up vertically, it's just going to be the same thing turned 90 degrees. Okay, not a big deal. All right, next is a box plot. They want us to do it like right next to it so I can compare them and see what I can tell from each one. So I'm going to use this exact same number line. I'm not even going to rewrite it, okay? And let me put it right above it. So I'm going to say I'm going to use this dot plot and I'm going to put it below. Fine, I'm doing above. I need more room. Okay, so we know that there were 2 number 1s, so dots, right? 2 number 1s. We know that there's a 5, 6, and an 8. 5, 6, and an 8. We know that there's a 10, 11, and 13. 10, 11, and 13. And we know that there's a 20. So that's what my dot plot looks like. All right, so what do I do with that? Well, think about this. Again, if we were trying to break all these people up into quartiles, right? We said the first quartile went to about 3. So what we're really saying is that 25% of the people fit within this range. And then there's another 25% that fit within the next range, which would be from 3 up till 8 about. So there's about 25% of those numbers fall there. then the next numbers go up until about 12. There's about 25% of our numbers, and then there's about 25% of our numbers. Notice that they're not all the same contained little boxes. There's a bigger box on the right-hand side because we had to stretch it out to get those 2 dots in there, right? Because they're still just 2 dots, right? They're still 25% of the numbers that we actually had, all right? All right, so let's see what else we can do. If I asked you a simple question about this and I said, what percent of these numbers that we just used, these numbers, fall between 1 and 12? What percent? Question mark. What percent go between 1 and 12? Well, 1 was our lower box, right? So that was a quartile. And 12, oh, I just can count up the number of boxes and use 25s and say approximately this many, right? We could use that to approximate. So if I started here and I went all the way up to 12, let's see, what would that end up being? If I start at 1 and go all the way up to 12, that would be 3 quartiles, which would be 75%. So about 75% of our data points would fall between 1 and 12, okay? What do box plots show us about the observations? What can't they show us? So in green, we have the original box plot. In blue, we have the box and whisker plot. What can we see? Well, the green is more exact. It gives us more details. We can actually see that there was a double number 1. We can see that there was a 20. We can see that it's relatively flat, that everything pretty much had 1 value to them. In a box and whisker plot in blue, I can't see how many numbers created those box and whiskers. The only numbers I know for sure are my max and my min that were in the original plot. That's it. Everything else has been calculated somehow or another, right? I don't even know for sure if that middle line is an actual number, because if there were 2 in the middle, we would have averaged them. So the only numbers I can tell for sure from a box and whisker is that there's a max and a min. And even if there were 2, I wouldn't put 2 dots over down here at 1. It's still just the lowest value is a 1. That's it. So keep that in mind when somebody asks you to interpret a box and whisker plot, that you are not seeing where this data came from, right? So if it would have just been two big towers of dots, this would have looked very, very similar, and you'd have a hard time knowing what the original looked like, okay? So what do the box plots show us? So we know that the box plots are good for comparing to each other. So good to compare to other box plots. So if you drew another box plot under it, I could tell you that this median is higher or lower than another one right next to it. I could see it on the number line. I could tell you that the range is bigger or smaller on another one that goes from here to here. So I can do good observations with another box plot of the same type, okay? But what I can't do is I can't tell what the originals were. And I also can't tell what their distribution looked like. Distribution is just how did those numbers get distributed across the number line. So I can't tell what their distribution looks like. Okay. All right, next part says, describe a box plot using calculators. We're gonna skip this for right now because we are still working on trying to get you guys a pickup date to come and get some graphing calculators before we start doing some of that, but we will show you it. All right, next one is, what is the difference between modified and regular? Okay, this is pretty easy. Regular is every dot gets used normally. Used. This one does the check for outliers. So now we can show you what that outlier thing looks like for the check for outliers. All right, so let's go back to this original and check for outliers, right? So if we were checking for outliers, we would have had to do Q3 minus Q1 to get our IQR. So let's see, Q3 minus Q1. Let me go back and look at it. It looks like 12 and 3, so we have 12 minus 3, so our IQR is 9. When we multiply that by 1.5, I'm going to get 9 plus another 4.5, that's 13.5, something like that, I think. Wait, did I do that wrong? I think I'm fine. Okay, let me just double check. So Q3 was a 12, Q1 was a 3, that's 9. Yeah, I'm okay. Okay, so that's 13.5. So if I want to check for outliers, where do you think we are likely to have an outlier? Look at that box plot, look at the dot plot, look at those two graphs, right? It's more likely this 20 might be an outlier than it is for the other end. We can check both, but I'm more worried about the 20 being an outlier than anything else. So let's go check that one. So I'm going to start out with Q3, and I'm going to add 13.5 to it. So Q3 was 12. And if I add 13.5 to it, I get 25.5. That means if any of my data points are above 25.5, they are considered an outlier. So our highest point 20 is less than 25.5, so it doesn't make it over the border to be called a outlier. So there are no upper outliers. No upper outliers. Okay, and then if I wanted to check the lower outliers, I would have started with Q1 minus 13.5. 1 minus 13.5 would be a negative 12.5, right? So I don't think we're going to have any numbers that are lower than negative 12.5, okay? All right, so this one shows the outliers, the modified one. The regular one does not. So how do I show an outlier? Okay, if I had a number that didn't pass, so without me going back and changing all of the numbers, let's pretend that the 20 was replaced with a 40. And yes, some of the numbers would change, the IQR might change, all of that might change a little bit. I'm going to just use these numbers just to give you an idea. We agree it would now fail, that 40 would be past the border on the right-hand side. It would cross. So 40 would be an outlier. Okay, so if our original list didn't have a 20, but it had a 40, then on my box plot, this maximum number is a dot, but it doesn't get the line that goes with it. It just goes down to whatever the next smallest number was. So what was the next smallest number that we had in our list? It was a 13. Did a 13 make our border of our line? No. It went a little bit out, so I go out this far and I number it as a 13. And it looks like that. Okay, and then on the other side, it just goes back out to whatever the lowest number is. So there's going to be a little gap. And this dot is kind of going to be out here all on its own. Okay, and the only numbers that display on a box plot are the numbers from the actual list, right? So I'm not going to make it at whatever the Q3 was. What was Q3? It was a 12. I'm not going to use that one as my border. I'm going to use the 13 that went just barely past the 12 number for the Q3, for the box. Okay, so I'm just going to put a little stick out there that just ends at whatever the number is that was okay and was not considered an outlier before it. All right, cool. We've got that done. Let's move on to our next one, which is standard deviation. Okay, and I actually think I'm going to start a second video for this because I see that the time is a little bit long and we might split this into 2 days. So give me a second here. We're going to close this one off. We're going to start another one just with standard deviation. All right.